I said we're going to move pretty quickly because I want to get through. It's a short day today. We only have 30 minutes, and I have about 37 slides. And I just want to cover the material. It should be pretty rapid because it's the homework that was due yesterday. A lot of this doesn't take a lot of heavy thinking. A lot of them you're going to see as a process. And man, after the second or third one, you're going to be bored. But guess what? We've got 9 more to go. And it's the same thing every stinking time. So if you can't do it the first time, hopefully by the 9th time you can do it. If you can't do it the first time, you're going to be like, I can't believe he's going over every one of these. There will be someone in the class that's saying, thank you for going over all 27 of them. Okay, here we go. Review question 1. What are valence electrons and why are they so important in chemistry? I was actually going to do kind of make this an activity. We can still do this. Guess what, Molly? Okay, before you answer the question, pass off for the second question. No stress. Just do it. Don't think about it. That's why we almost used a beach ball, because you don't worry about like throwing it to someone and not calling their name. Like it bounces off them. That's fine. I was going to bring a balloon and then make the rule that if you break the balloon, you get every question from there on out. Because I knew if I brought in the balloon, somebody over there would break it. Okay. So Molly, what are valence electrons and why are they so important in chemistry?
Valence electrons are electrons that exist farthest from an atom's nucleus. They are the electrons with the highest energy level number. They're important because an atom's chemistry or chemical behavior is determined mostly by the number of the valence electrons.
Right. So take away from that. Why are they important? Because the chemistry of the atom is based upon its valence electrons. How it's going to behave chemically is based upon the valence electrons. And how do we determine the valence electrons? Well, the second question says, how many valence electrons are in the following configuration? So again, Madeline, we'd pass that off and then go ahead and answer the question. There you go. Kelly. So in this electron configuration, I need to figure out how many valence electrons that configuration represents. 5. And how did you come up with 5? Okay, the highest energy level, and the highest energy level here is what energy level? Say the 5th energy level, right? We look at where the 5s are. The highest numbers are 5s. The 5 is the coefficient in the front. 1st energy level, 2nd energy level, 3rd energy level, 4th energy level, 5th energy level. So we see a 5. Usually going to look all the way to the right at the end, and then make sure that, like for example, if the d orbital was being filled, you'd have to look back a little bit to find if there's a higher one just before it. In this case, the 5th energy level has 5 electrons in it, 2 in the s orbital and 3 in the p orbital. So there are 5 valence electrons. Remember that this d orbital is not part of the valence. Those electrons fill later, but they're actually in the 4th energy level, not in the 5th energy level. Okay? Go ahead and pass off the towels, and we'll go ahead with review question number 3, which says, the chemistry of life is based on carbon. Okay, this is my paraphrase of the question. Chemists often speculate concerning silicon-based life forms. Why is that, ma'am?
Because silicon is the closest element in chemical behavior to carbon.
Right. Remember we said carbon is a column 4 element. It has 4 valence electrons. The chemistry of every other column 4A element is very similar to carbon. So we can speculate that we could switch out a carbon for not only silicon, but what else? Let's say that we knew that let's say we did discover silicon-based life. What would be another basis of life we might look for? If it's not carbon-based or silicon-based, what would be next? What's the next element in column 4? You got carbon, silicon, germanium, right? We just go down the column 4A elements. It could be any one of those. Why? Now that we've done a little bit of covalent bonding, we recognize that every one in column 4A has 4 unpaired electrons around it. It's going to have the same basic chemistry, extremely similar chemistry as a carbon. And since we understand, or think we understand, carbon-based life form, I just pull out something with 4 connecting points, I stick another one in. Pull it out, stick another one in. I do some genetic engineering. And I replace carbon with silicon, and I replace it with all the other column 4A elements. And we speculate that that might work. It's the closest thing to what we know. Was there a question? Okay, no? Did you pass? Go ahead and pass it off, and we'll do number 4. So number 4, what are the noble gases and why are they important in chemistry?
They're the atoms in column 8A of the table, and they are important because they have the ideal electron configurations in nature.
Right, they have the ideal electron configurations.
In the front of the book on the far right, it had A or UUO as at the end. Does that count as one too?
UUO?
It added art underneath.
Oh yeah, there's other elements that frankly they get discovered and things like that. But right now we're just looking at the noble gases. There actually are some tables that have elements in them that have not yet been discovered yet, but they know when they're discovered they're going to fit in those places. Okay? Remember we said before that the table of elements that we have now started with a whole bunch of gaps. There was a pattern, and when they figured out the pattern and they placed them on the table, they had gaps, but they knew when they found it, they knew it would go in that place because based upon the proton count. They just knew that's where it was going to go. So, noble gases, right, they're column 8A. They're also called inert gases. They don't react, and they don't react because they already have the ideal electron configuration. Okay. Pass it on, and number 5. What is the octet rule, and give 2 exceptions?
Most atoms strive to attain 8 valence electrons, and then the exceptions are hydrogen, lithium, beryllium.
Right. We have hydrogen, helium, lithium, and beryllium are actually the 4 exceptions. That's why it's, the way they say it in the book is all atoms strive to have 8. The exceptions are. The way I want you to remember it is virtually all, or most all, the exceptions are. Because if you just remember the all atoms, you will get it wrong. You have to remember the exceptions. So just memorize it as virtually all atoms seek to have 8 valence electrons. The exceptions are hydrogen, helium, lithium, beryllium. Why are they the exceptions? Because they are trying to go to 2, not 8. Everybody else strives to go to 8. They're trying to fill the 1s2 positions, 1s1, 1s2. That's where they want to stay. Everybody else wants to fill the s and p orbitals in their energy level. Okay? So you have the next one. Pass it on. Here we go. By the way, you can't get it twice before everyone's had it once, so don't try to hide in a corner somewhere. Okay, this has multi-parts, so let's do part A. Draw the Lewis structure for the following atoms, and there are several of them. What are we going to look for here?
How many valence electrons?
Well, how many are there in that atom?
4.
How did you know?
Top of the column, it said it had 4.
It's a column 4A element, isn't it? Column 4A elements have 4 valence electrons. All right, pass it on. Here we go for B. So the element is Te. Don't worry about the names. I'll just give the letters. Te is Te, not Te, Te. 7, because you found it where? Column 7A, right? Oh, it didn't work, did it? Is it in column 6A? Yes, it's in column 6A. Yes. Okay. So it's in column 6A, so there are 6 valence electrons. All right, pass it and ready to answer. C. Part C. There are 2 where they would be placed. Where would they be placed at? Where am I going to put them?
At the top. At the right at the bottom.
Okay. Start at the 3 o'clock position. 3, 6, 9, 12. That's just standard practice. Now we know when we go to form a molecule, we can arrange that a little bit differently. You know, we can put unpaired next to unpaireds. That's fine. But when you're just drawing this Lewis of 1, start at the 3 o'clock and work your way around. All right, next. Ooh, who's next? Stephen. So the chemical formula for aluminum sulfide. We're going to walk through this. What are the 2 elements that are in play here? And this is kind of the process. This is one of those ones we're going to go, another one like that? Yeah, I want you to see the pattern. I want it to be like ingrained in you. I encourage you to do it this way. If you don't do it this way, make sure your way gets you to the same right answer, the same right place. So we've got aluminum and sulfide. What are the two elements we're looking at for aluminum sulfide? Aluminum and sulfur, right. So we know the two elements that are in play. We've got the metal aluminum and the ide, which is means we're going to have an ion of the nonmetal. Sulfur is sulfide. What do we do next? Well, now we're going to look at the charges, right? What ionic charge do these molecules seek? What do they want to have? And so aluminum wants to go to what charge? Okay, it wants to eventually be 8, but it's in what column now? So look above the column where aluminum is located. It's right over here. Okay, so it's in column 3A. A column 3A element wants to have 8, but it has 3. And since it's a metal, rather than building 5 more to go to 8, it loses 3 to go to 8. Metals want to give up electrons. So it has 3, it wants to give up those 3, and that produces a +3 ion. Sulfur, however, is what column? Column 6. It wants 8. It's going to go from 6 to 8. It's going to gain 2 to get 8 as the nonmetal. When it gains 2 electrons, it's going to have a charge of 2 negative. Okay, so those are the charges of the ions that are formed. Aluminum wants to go to 3 positive, and sulfur wants to go to 2 negative. And when it's 2 negative, now it's a sulfide ion. Here it's a sulfur atom. Here it's a sulfide ion. Here it's an aluminum atom. Here it's an aluminum ion. Remember, the metal keeps its name. It doesn't change. So I have an Al. Aluminum wants to become 3 positive, and sulfur wants to become 2 negative. So what is the formula for the molecule that's going to be formed? Do you know that? Very good. Al2S3. I know that because I look to the charge, I ignore the sign, pluses and minuses, and I transpose the signs as subscripts across diagonally. So the 3 here becomes a 3 subscript to this element, and the 2 here becomes a subscript to this element. Now I do a quick check. What I do, and this is where I'm explaining the process. We're going to zoom through the rest of these, but it's the same process, okay? What I'm going to do now is do a mathematical check. Remember, we're trying to balance the charges. They're opposite but equal, because we want the molecule to be a net neutral charge. The way I do that mathematically is I ignore the pluses and minuses because I recognize I've got a plus and a minus. But here's how it works. I have 2 atoms at a +3 charge, and that must equal 3 atoms at a -2 charge. Does 2 times 3 equal 3 times 2? Yes, it checks. We're right. Okay? Now there's one other caveat we checked in here. I did, but maybe we didn't mention it. But when I write this with the subscripts, I need to make sure that there is no common factor. And if there is, I need to reduce the numbers by the greatest common factor. That's one more point. So, who's up? Okay, pass it on. Here we go. The formula for iron 1 nitride. Okay, so the elements in play are iron and nitrogen, right. But iron and nitrogen, those are the elements. What are the ions in play? Well, the iron ion and a nitrogen ion, right? The nitrogen ion we know as nitride, right? Okay, so iron and nitride. What are the charges that these 2 atoms want to take on? What is the charges of the ions of iron and nitrogen going to be? Now, no thinking involved in iron, right? Because they tell you right there. So what is it? 1. The metal wants to go to a 1, and the charge is going to be positive because the metal is giving up electrons. So the charge here is going to be an iron Fe 1 positive. What about nitrogen? Okay. It's column 5 element. It wants to go to 8. By gaining 3, makes it 3 negative. So I have an iron 1 positive. That 1 positive isn't because it's column 1. That 1 positive is because they gave you the information that they're using this particular ion of iron. It's iron 1 nitride. No thinking here. Iron 1. How do you know? They told me. Nitride is N. It's a 3 negative. How do I know? It's a column 5 element. It wants to go to 8. It wants to gain 3 electrons. It becomes 3 negative. What's the formula? Fe3N. Let's check it. 3 ions at +1 equals 1 ion at 3 negative? Yes, it's true. We're done. Fe3N for iron 1 nitride. Pass it. Here we go. Who hasn't had it yet? Nobody? Here we go. Magnesium oxide. I'm way behind in my notes, so let me get up there. Okay? Magnesium oxide. What are the two atoms, two elements in play? Magnesium and oxygen, right. So magnesium and oxygen are in play, but not technically the atoms or the element magnesium oxygen, but the ions of magnesium and oxygen. So what is the magnesium ion going to have? What's its charge going to be? Positive 2. It's a column 2A element. It's going to lose 2 to go +2 charge. What about oxygen? Mm-hmm. Okay, what column is it in? Column 6? It wants to have 8. So how do I go from 6 to 8? 2. I gain 2. I gain 2 negatives. It has a charge of 2 negative. Okay? Do you get that? Okay, so magnesium wants to lose 2, it becomes +2. Oxygen wants to gain 2, it becomes 2 negative. So what is the formula for this molecule? Okay, it's just Mg2O2, but we need to look for the greatest common factor, don't we? What's the greatest common factor between 2 and 2? 2. 2 is the greatest common factor between 2 and 2. So we reduce Mg2O2 to simply MgO. Okay. Was it a question or?
That's what I was going to say. Is it when the twos like cancel?
Mm-hmm. I look at this, and if this were, and there's another one where it gives this example, but do you see here that the factors of 2 are 1 and 2, and the factors of 2 are 1 and 2? So the greatest common they have is 2, and I reduce both of them by dividing by 2, and they become Mg1O1, which we don't show the ones. Okay, now we'll check it real quick. Magnesium, I have 1 magnesium at 2 positive. Is that equal to 1 oxygen at 2 negative, given that the charges are opposite? Do the numbers match? Yes, so we have equal and opposite charges. The net charge of the molecule is 0. That's correct. All right.
There's 2 left.
Oh, I've got more. Don't worry, there's more than 2 left. Chromium 3 oxide. The elements in play. Chromium and oxygen, good. The ions in play.
+3.
You know that because? Chromium is 3 positive because it's given to you, right? And the oxygen? That's it. Chromium is 3 plus. How do I know it's a 3 positive? They gave it to me. Oxygen is 2 negative. How do I know? It's a column 6 element. Wants to go to 8, needs to gain 2, makes it 2 negative charge. What's the formula?
Cr-2O3.
Okay, drop the negatives and positives, right? You don't need that. So it's CrO. Yep. Let's do the math check. Given that they're opposite charges, but does the magnitude match? 2 atoms at +3, or 2 at 3 is 6, and 3 at 2 is 6. That statement's true. The molecule neutral charge, we're done. Okay? Who's next? Pass it. Here we go. Practice problem number 3. Which atom gives up its electrons most readily? Now, before we answer the question, because they give us some options, right? But let's reword that in a way that we actually studied. What are they asking for here? What are they asking? Which atom gives up its electrons most readily? What does that mean?
Which atom has the least control over its electrons?
Least control, okay, has the least amount of, it's gonna assert the least amount of force to keep it, right? Right. What is that force we talked about? That is the force to keep what I have. And I said there's two forces that we talked about. One is the force I exert to keep what I have. The other one is the force that I exert to take what somebody else has. This one is asking which one is applying the least amount of force to keep what it has. What is that force known as? Try again. Okay, good. Ionization energy, right? The ionization energy. I want you to remember, ionization energy is the perspective of how much energy am I going to exert to keep what I have. Usually that's applied in this way. How much energy is somebody else going to have to exert to take what I have? They're going to have to use just a smidgen more than I'm using to hold on to it. Okay? So ionization energy, start by thinking from the perspective of the, I'm going to keep what I have. And so the question here says, which one gives it up the easiest? Well, the one that gives it up the easiest is the one that holds on to it the lightest, right? And we're given 4 options. Now, what we're going to do, since this is known as a periodic property, we're going to go ahead and plot them on a periodic table. So the 4 different atoms we're talking about now in play are Al, B, In, Ga. Now, what is the periodic trend for ionization energy? I'm still over here. This is all one question. Up and to the right. That's the trend. Now, the question was, which has the least? So if it trends up and to the right, increasing, I'm looking for what is to the lowest and to the leftist. So what's the answer? In. Of those 4 that I have picked from, the one that holds on with the least amount of force, which means it's the easiest, most readily gives it up, means every other one of these fights to keep it more than this one does. Okay? Is that clear as mud? Like we're good? Which one? And we're going to do more ionization energy and other things tomorrow when we do review. We have about 7 minutes now, and we're going to cruise on to the EPPs. So these will be pretty quick because they're repeats of what we've just done for the most part. So whoever is next, pass it on, and here we go. Draw the Lewis structure for the following atom, Sr. I think it's strontium, but frankly, there's a lot of these I don't use very often, so I tend to forget them. But that's why I tend to just also say Sr. Okay? So what is the Lewis structure for the element whose symbol is Sr? Okay, so we just say you have 2 valence electrons, right? Because it's in column 2A. And I see that you recognize that. You've seen it. So we start placing them at the 3. Remember, the pattern is 3, 6, 9, 12, 3, 6, 9, 12. Just follow around. We need to place 2, so we place it at the 3 and the 6. There we go. All right? Pass it, and here we go. The second one, part B. Lewis structure for Kr. Krypton. What does the Lewis structure look like for krypton, ma'am? Because it is a noble gas, column 8A. It's at the lowest energy level because its valence is full. Its octet is satisfied. Okay? Pass in next. Here we go. S, sulfur. Where's it located, ma'am?
6A.
Column 6A. How many valence electrons? 6. So where are they going to be placed? Let's just walk around it, okay? Let's go. 3, 6, 9, 12, 3, 6, and we're done, right? There's 6. So remember, if you're trying to draw it, you want to say, well, where are there going to be doubles? How many more than 4 do I have? 2. Okay, so my first 2 places are going to be doubled up. 3, 6, 9, 12, 3, 6. There's all of my valence electrons. Okay, pass it, and here we go. Next one. Bi. B5, that you're saying it's a column 5A element? Okay. And they'll be placed where? Where will the double be? 3 o'clock position. So we have a double over there, but we're still going to count them around. And you're going to pick that up because I'm leaving a gap for that. I'm not going to put in an animation and slide the dot over as we go around. That's just too much. Too many clicking. Okay? So there's your Lewis structure for Bi. Pass and next. Here we go. 2A. Give the chemical formula for the following molecule. Aluminum oxide. Pass it. Pass it. There we go. Okay. So the two elements in play are aluminum and oxygen. So the two ions in play are, what are the charges?
Aluminum is, I think, +2, and then oxygen is -3.
And try again. Aluminum is in what column? 3. It's a metal. It wants to lose its 3. It becomes 3 positive. Oxygen is in column 6. It wants to become 8. It needs to gain 2. So the charges are Al3 positive and O2 negative. From here then we figure out the formula, which would be Al2O3, right? And we do the check by saying I've got 2 ions at 3 positive. Does that equal 3 ions at 2 negative? Yes, it does. Okay. Next, pass it on, and here we go. Calcium sulfide. The 2 elements? Calcium sulfur. The 2 ions?
Calcium is 2 positive and sulfur is 2 negative.
Okay, so we've got 2 positive and 2 negative. Formula?
CAS.
Correct, CAS. Do you see that it would be Ca2S2? However, they have the common factor of 2, so it reduces down to CAS. Do the math check. I've got 1 calcium at 2 positive, and that equals 1 sulfur at 2 negative. It checks. Okay? Pass, and here we go. Beryllium carbide. The 2 atoms in play, or 2 elements in play. Who's answering, by the way? You, okay, him. Beryllium carbide. The 2 elements are beryllium and carbon. The 2 ions, however, that make up this molecule are beryllium, what? What's the charge of the beryllium ion? You're going to say beryllium 2 positive because it's the metal and it gives up. What about carbide or carbon? Okay. Carbon is a column 4A element, and it wants to go to 8, and it's a nonmetal, so it gains. It goes to a -4. The formula.
Well, it would be BE4 and C2, but do you like?
Yes, you do. It would be Be4C2, but you know that the greatest common factor between 2 and 4 is 2. And so you reduce every one by dividing it by 2, and you end up with Be2C. And we'll do the check. Beryllium, I have 2 ions at +2, and carbide, I have 1 ion at -4. It checks. We're right. Okay, pass, and here we go. Potassium nitride. Potassium and nitrogen. The ions in play. +1 and okay, so it's a column 5A element. It wants to go to 8. So to go from 5 to 8, I need to add 3, and that means I have a -3 charge. So what is the formula now? K3N.